So how do we make amines? A lot of times, much of amine synthesis involves reducing another nitrogen-containing functional group as our final step of the synthesis. So if I can make a nitrile, right, which has a C triple bond N in it, or if I can make an amide, right, a C double bond O NH2, I can reduce either of those to form an amine that's next to a CH2 group in both cases. In the nitrile, the C of the triple bonded N becomes the CH2. In the amide, the C double bond O becomes the CH2. So take a look at the synthesis. If I have an alkyl halide, I react it with sodium cyanide, which is a source of Cn minus. We can undergo an SN2 reaction. Cyanide is an excellent nucleophile that will displace a leaving group. Just an SN2 reaction. We have an alkyl cyanide, or more commonly known as a nitrile. Lithium aluminum hydride, followed by water or acid as the workup, will give us a primary amine. We're essentially adding two equivalents of hydrogen across that triple bond. So we're filling up that triple bond with hydrogens. If we can start with a carboxylic acid, we can use thionyl chloride to make the acid chloride. We can use ammonia to make an amide, to make just a primary amide, like that. So RC double bond O NH2. Reduction with LAH here will give us a primary amine that way also. The nitriles are limited to forming primary amines only. But amides can form any type of alkyl substituted amines. Okay? Turns out we can at least form primary, secondary, or tertiary amine starting with an amide. So if I react acid chloride with ammonia, okay, I end up with just an NH2 amide. With lithium aluminum hydride, I end up with a primary amine, RCH2NH2. If I react a primary amine with an acid chloride, I get an amide with one R group attached. Lithium aluminum hydride gives us RCH2NHR prime, which is a secondary amine. Getting two R groups in that amide, reducing it, gives us RCH2N, and that N has two other R groups on it, but because of the first R group there, that is a tertiary amine. So, very general method for making primary, secondary, or tertiary amines. As long as we have one CH2 next to that N, retrosynthetically, we could think of that CH2 as coming from the carbonyl of an amide. In electrophilic aromatic substitution, we've already seen this earlier, but it's good to review. It's been a while, right? If I have a nitrobenzene, I can reduce it to an aniline. So that nitro, that NO2 group, can become an NH2 group with various reducing agents. So hydrogen with a catalyst, platinum, palladium, right, whatever. The hydrogen in a catalyst will reduce, right, it'll convert the nitro group to an NH2 group. If I want to use tin 2 chloride, SnCl2, what can happen then? That nitro group will be also reduced to the amino, to the aniline, but it can do that in the presence of other groups that might be reduced otherwise. Right? That tin selectively reduces a nitro group instead of any other group that could be reduced. So that's useful. The amine itself acting as a nucleophile in an SN2 reaction is not very useful to us. Why? Take a look with ammonia here. We can very easily react it with an alkyl halide to get one R group attached, right? First we have a ammonium salt right there, but a little sodium hydroxide will deprotonate, we get primary. But now this primary amine, remember we said that as we add R groups, the amine becomes more basic. Let's say more reactive. because the N is acting as a nucleophile in this reaction. So the subsequent alkylations, right, once we react with one, the second one will happen even faster. And then the third one will happen even faster than that. So there's no way to just stop it at alkylating only once. Right? Even if we try to control one equivalent, we'll have some of them reacting all the way and then a lot of NH3 just left over. So the only thing this is useful for is if we want to make a quaternary ammonium compound, where I want to have 4 R groups on that N, in which case we just use excess of the alkyl halide, right? Use plenty of that around and we'll exhaustively alkylate an amine. They become more basic, the more substituted they are. Subsequent alkylations are faster than the initial alkylation. So don't just expect to use NH3 with some alkyl halide to get a single alkylation. You can't, it doesn't stop. Instead, I think what the most versatile synthesis of amines is, and you can make any amine this way, pretty much, if it's some kind of alkylamine. It'll start with a ketone or aldehyde. So that's this right here. This is just a ketone right here. What we do is start by just reacting that ketone or aldehyde with an amine. And we saw in our ketone aldehyde chapter that what you get when you have this ketone plus NH3, for instance, is an imine, R, C, R, and then C double bond N with one H on it. Make sure your nitrogen stays neutral, right? Don't give it too many H's. So the imine then can be reduced to a primary amine. We essentially add hydrogen across the CN double bond, right? So now I have a primary amine. I have RCR, we have a CH, and we have NH2. Now, that C triple bond N became a C single bond, and we added hydrogens on either side of it. If I start with the same ketone, with this time an R group, so methylamine or something like that, our imine will look like this, RCR double bond N with whatever our other R group was. Reduction of that gives us a secondary amine, right? That other R group came from the amine that we used before. If I use a amine with 2 R groups on it, what we get is R, C, and then N has 2 of its own R groups. So I can't make a CN double bond. I have to make a CC double bond. This is an enamine. It would be helpful if you looked back in the ketones aldehydes chapter and reviewed imines and enamines. But that enamine then is easily reduced because it's just adding hydrogen across that CC double bond. That's it. And that's how we get a tertiary amine, right? The nitrogen has 2 R groups on it that we introduced to make the enamine. The other R group came from the carbonyl compound, and now we have a CN single bond. The mechanism of this is sort of an abbreviated mechanism, but the amine attacks the carbonyl, which gets protonated. We end up with this carbonyl amine. Right? It's an NH2 with an OH attached. If we further protonate that hydroxide, we can lose water. Okay? And if I do a proton transfer, this is how I get the imine. And an imine has a CN double bond right there. Reducing agent then will add hydrogen across that CN double bond, giving us our regular old amine. So very, very useful compound. It's called reductive amination. Okay? Not animation, but amination. It's hard to say, right? So take a look at just a simple example here. This is one way amphetamine is made, right? If I have phenyl 2-propanone, right? Phenyl CH2 C double bond O CH3. If I react it with ammonia and a reducing agent like hydrogen with a catalyst, that carbonyl becomes a CH-NH2. We've introduced a nitrogen with no further alkyl groups, attached to it. That's what we get when we add NH3. The intermediate imine was PHCH2 C double bond N with an H on it, and then CH3. So let's take a look at these three compounds and retrosynthetically decide how to make them by reductive amination. All we need is a carbon with an H on it next to the N. Okay? So that bond is the one that's formed in reductive amination. So in this case, we can go in two possible places. Okay? To do that first one, we would have to have CH3, CH, double bond O. We need an aldehyde. Okay? Where that carbon-nitrogen bond is now, there was originally a carbonyl plus extra hydrogen on that N, but CH, CH3, CH3. Okay, that's one. Or if I did this other one, I have, if I want to break this one, we have the amine, CH3, CH2, NH2, and acetone, right? 3 carbons. The carbon now attached to the N was originally a carbonyl, so there's acetone. This next one, N-ethyl aniline, we can't break the N-benzene bond because there's no H on there. In other words, we can't start with a carbonyl on benzene. Benzene can only have one substituent per carbon. So we have to break that bond right there. That's the only one we can break. So that has to start with aniline plus acetaldehyde, HC double bond O, CH3. Notice our final product has an additional H on the C, and it has essentially lost an H on the N. Yeah, that's right, because the intermediate imine, if you wanted to draw that, would have no H on the N, it turns out. So in this one, this is N-methyl cyclohexanamine, or cyclopentylamine. Yep, 5 carbons. So this one we can break on either side of the N retrosynthetically. 2 options. Let's do this one over here, the cyclopentanone plus methylamine. Or the other way, cyclopentylamine plus formaldehyde, a 1-carbon carbonyl compound. Okay? So for practice, show how each of these makes an imine, which is then reduced to make these compounds made by reductive amination. By the way, you can skip the Hoffman rearrangement and the Curtius rearrangement. They're actually very important reactions, used quite a bit, but they're complicated mechanisms that we don't have time to learn at this point in the semester.